Welcome back to the deep dive. We are jumping straight into the engine room of modern AI today, and we're tackling a really fundamental question,
The big one.
a huge one. How do we get these large language models to handle high-stakes, verifiable reasoning? I'm talking complex math, physics, structured code without, the astronomical compute costs that come with them.
That is the trillion-dollar question, almost
Yeah.
literally. LLMs have this incredible potential for deep reasoning, but to get that reliable, objective correctness, it takes specialized work after the pre-training.
And that work is expensive.
Intensely resource-heavy. It demands these intricate optimization routines that have to work over massive, massive parameter spaces.
And the method that unlocks this higher level of intelligence, is something called reinforcement learning with verifiable rewards, or RLVR.
Right.
This is the step that takes a model from just sounding smart, which supervised fine-tuning or SFT is pretty good at, to actually being objectively correct.
RLVR is absolutely essential because it introduces a hard, objective truth. With SFT, you're basically asking the model to mimic the style and content of a huge data set written by humans.
Yeah, it's just copying.
But when you need to solve a brand new math problem, mimicry isn't going to cut it. You need objective, deterministic verification. A code checker, a math verifier, something that gives that binary feedback. R equals 1 for correct, R equals 0 for incorrect.
A simple thumbs up or thumbs down.
Exactly. And that verified signal is what truly drives the sophisticated reasoning. It lets the model go way beyond just rote knowledge.
So SFT gives them the language, but RLVR gives them the brain to use that language correctly. But that verifiable reward, as accurate as it is, it's inherently sparse. And that's the root of the whole efficiency problem, isn't it?
It is the defining bottleneck. I mean, think about the contrast. SFT gives you dense supervision. Every single token you generate during SFT can be compared to a target token. You get constant, dense feedback.
Teacher forcing.
But with RLVR, you get a sparse one-bit reward. A single binary signal that only arrives at the very end of a long, maybe multi-step chain of reasoning.
So you generate 500 tokens of some complex math derivation, and all you get back is a yes or a no.
Exactly. It's like training a complex organism where the only feedback is whether they survive the final challenge or not. And that sparsity has a profound implication for efficiency.
How so?
If you try to do full parameter RL training, updating billions of weights based on that single bit of information, you get massive parameter redundancy. The signal is just too localized, too specific to justify updating the entire network's geometry.
Which is where parameter-efficient fine-tuning, PEP, comes in. I mean, these methods, especially LoRA, were designed for exactly this. They let us adapt models using just a tiny fraction of the parameters.
And this is where the research community, kind of fell into a common trap. Because standard LoRA works so well for FFT, the dense reward world, it just became the unquestioned default for RL.
The easy choice.
It was convenient. But the fundamental optimization challenge for sparse RLVR is a completely different beast.
So the core mission of this deep dive, then, is to move past that default. We've gone through sources covering this huge evaluation of over a dozen PEFT methods on really hard math reasoning tasks using the most advanced RLVR algorithms.
Right.
We need to find which architectural choice is truly optimal for the unique dynamics of sparse RL.
We're trying to provide a That's where the foundational framework comes in. Group Relative Policy Optimization, or GRPO.
Okay.
Most standard RL algorithms need a separate, highly complex neural network, a critic, to estimate the value of every state or action.
Which is computationally expensive.
Very expensive. And it brings its own set of stability problems. So GRPO is a really smart workaround.
How does it work?
It gets rid of the critic model entirely. Instead, it estimates the advantage, how much better or worse one response is compared to its alternatives, just by using group statistics from the reward signals in a small batch of generated responses.
Wait, let me make sure I understand the intuition here. So if you prompt the model with a math question, it might generate, say, 10 different answers.
General outs, yeah.
And GRPO doesn't just look at the one that got the check mark. It looks at how good that one correct answer was compared to the 9 that failed.
That's the core concept. The central part of the GRPO objective is calculate what's called the standardized advantage, ani prisol. For any specific response, you take its reward, you subtract the mean of all the rewards in that group, and then you divide by the standard deviation of those rewards.
So if I get a reward of 1, but the average reward of the group was, say, a 0.9, because 9 out of 10 attempts were also correct, my advantage is actually pretty small.
Right. The policy doesn't need a huge update. The update will be mild. But if you get a reward of 1 and the group mean was 0.1, meaning only your attempt was right, that response is highly advantageous.
So the system knows to aggressively reinforce the path that led to that one success.
Exactly. That standardization makes sure the policy updates are driven by the relative quality and the difficulty of the problem. It's a brilliant way to stabilize training, especially when getting a correct answer is rare.
But the research also points out that even GRPO has some practical stability issues, especially with the really long chains of thought needed for complex math.
Yes, and these challenges led to some crucial algorithmic refinements. We should probably discuss two of the most effective ones highlighted in the research, starting with DPO.
DPO, decoupled clip and dynamic sampling policy optimization. What problem was it trying to fix?
So DPO primarily tackles training instability and this risk of entropy collapse.
Entropy collapse.
Yeah, sounds bad. It is. It's when the model's policy just collapses into a single, predictable, and often suboptimal line of reasoning. It stops exploring better paths.
It gets stuck in a rut.
Exactly. So to fight this, DPO introduces a clip-higher strategy. It basically decouples the policy clipping range you normally see in PPO. They use a much larger upper bound for clipping, an epsilon high of 0.28.
And what does that larger clipping range actually mean in terms of the model's behavior?
In simple terms, it gives it substantially more headroom to uplift low probability tokens during optimization.
So if the model tries a weird long shot token that actually leads to the right answer?
That larger clip allows the RL update to reinforce that choice much more aggressively than standard PPO would ever allow. This is vital for maintaining policy diversity. Complex math often needs non-obvious creative steps, and the model needs the freedom to explore those low-confidence paths if they lead to success.
That makes perfect sense. If you're solving a competition math problem, the first path you think of might be the wrong one. You need the freedom to try the third, weirder path that actually works.
Precisely. And DPO also uses something called dynamic sampling, which is a crucial efficiency technique. It filters out any prompt where every single generated output has the exact same reward.
So if they're all wrong, it throws it out.
Right, all zeros. Or, less commonly, all ones, all correct.
Wait, why would you filter out the all correct ones? Isn't that good data?
It's technically good data, but it provides a negligible gradient signal for improvement. If every reward is 1, the group mean is 1, and so the standardized advantage approaches 0.
Ah, see, you've solved it, but the policy has no idea how to get even better relative to itself.
You got it. Filtering these ensures the model only spends compute time training on inputs that give a meaningful, non-zero gradient. It dramatically improves sample efficiency.
Okay, so that's DAPO. Now let's look at the other major refinement, Dr. GRPO, which I found fascinating because it's all about fixing biases that were kind of accidentally baked into the original framework.
Dr. GRPO is so interesting because it tackles issues that look small on paper but have a massive impact. The research identifies two systematic issues. The first one is about the length of the answer.
The length bias. Tell me about that.
So the original GRPO formulation had a per-response length normalization term, 1 over the length of the output. The idea was probably to stabilize the magnitudes of the probabilities over different lengths. But it accidentally created this huge bias.
How so?
It penalized concise, correct answers by dividing their score by a smaller number, while at the same time giving a disproportionately higher weight to longer responses.
Wait, so the model was being rewarded for being wordy even if the long answer was completely wrong just because the math favored length?
If a correct answer was 5 tokens long and an incorrect answer was 50 tokens long, the normalization could unfairly amplify the advantage score of the longer incorrect answer. It's a huge flaw. Dr. GRPO just removed that term entirely.
Which would then promote clear, efficient reasoning. In math, you want the shortest, cleanest path to the right answer.
Exactly. Elegance and conciseness matter. The second bias Dr. GRPO tackled was difficulty bias.
Oh, yeah.
The original formula used the group-level standard deviation in the advantage estimation. This meant if a question was either extremely easy, so everyone got it right,
So the variance was low.
or extremely hard, so everyone got it wrong and variance was also low, that standardization could give those questions disproportionately high weights.
Because if the denominator is tiny, the overall standardized advantage suddenly explodes, giving this huge gradient signal to a question that was either trivial or impossible.
You got it. So Dr. GRPO removes that group-level standard deviation component. This makes sure the policy updates are driven purely by the actual relative value, not the statistical volatility of the question pool.
So we have this really complex landscape. a sparse one-bit reward signal, carefully refined by algorithms like DBO and Dr. GRPO. And this brings us back to efficiency. You said the sparsity creates massive parameter redundancy. Can you elaborate on why the updates localize so much?
Sure. Think about a complex math derivation. The model might use 10 distinct specialized facts or reasoning steps. If the final answer is wrong, the fix doesn't require relearning general language rules.
It requires correcting one specific logical step.
Right, maybe a single token choice 10 steps back. Because the signal is so targeted, a single correct or incorrect bit related to a specific high-level policy choice, the necessary correction often localizes to a very small set of weights. Researchers call them small subnets or sparse parameters.
So if the model is 7 billion parameters, maybe only 10,000 of them actually needed to be adjusted to fix that one critical reasoning path.
That's the intuition. The vast majority of the weights related to syntax, grammar, general knowledge, they're perfectly fine. If we insist on updating everything with full parameter fine-tuning, we are just wasting incredible amounts of compute and memory.
So PFT isn't just an optimization tool here.
It's a structural necessity for scalable RLVR.
Yeah.
We need a method that efficiently targets those sparse, localized changes without sacrificing the overall reasoning capability of the model.
Okay, so the research clearly suggests that standard LoRA, while it's the convenient default, is fundamentally suboptimal for this sparse, localized RLVR optimization. Let us quickly review standard LoRA for anyone who needs a refresher.
Sure, LoRA is really elegant because of its simplicity. You take the massive, pre-trained weight matrix, W0, and you freeze it. The entire goal is to only trigger the update matrix, delta W.
And LoRA constrains this update.
It constrains it by decomposing it into the product of two much smaller low-rank matrices, B and A. So the updated weight is just W0 plus B times A.
And the rank, R, is tiny, maybe 16 or 32 compared to the hundreds or thousands of dimensions in the original matrix. And that's how we get the efficiency. I mean, the trainable parameters for the DeepSeek models they tested dropped to, what, 1.55%?
A negligible amount. And critically, the standard initialization is where A is random Gaussian and B is 0. This means delta W starts at 0, so it perfectly preserves the original pre-trained policy. You only introduce changes as the RL optimization demands it.
But the finding is that while standard LoRA is efficient, it hits a respectable 42.5% average accuracy, but it still consistently trails full parameter fine-tuning, which got to 44.9%.
Right. So settling for the default means you are sacrificing crucial reasoning power. We have to do better.
And that's why the study's first major finding is so important, the superiority of what they call structural variance.
The core insight, really, is that PEFT methods that fundamentally alter the architectural formulation beyond that simple additive W0 plus BA product are the ones that consistently give you better reasoning accuracy.
Okay, let's focus on the absolute winner then, the one that broke the performance ceiling. DoRA, or weight decompose low rank adaptation. What is DoRA doing differently that not only helps efficiency, but actually improves the final score?
DoRA's innovation directly addresses what researchers call the optimization rigidity of standard LoRA. In standard LoRA, that low-rank update, BA, has to simultaneously capture both the direction and the magnitude of the necessary weight change.
Both at once.
Both at once. And for a sparse RL signal that's trying to make a complex nonlinear policy shift, forcing both into that single low-rank product is often just too restrictive.
Wait, so the low-rank constraint might be forcing the model to take a less optimal directional step just to get the required magnitude, or vice versa?
Precisely. DoRA solves this by decoupling them. It separates the magnitude of the weight vector, a scalar value, m, from its directional component, which is a normalized weight vector. The adapter BA then only updates the direction.
And the magnitude is handled separately.
The magnitude is handled separately. The updated weight becomes m times the normalization of W0 plus delta W.
That feels like giving the optimizer two separate, smoother dials instead of one complex, stiff dial. How does separating those two signals specifically help sparse RLVR find the right path?
Well, think back to that sparse signal. When the model gets an R equals 1 reward for a hard problem, the policy needs a massive, complex, directional shift. Because that signal is scarce, the gradient is often noisy or weak.
Okay.
If the adapter has to learn a huge magnitude and a precise direction at the same time, that weak RL gradient might fail to push the weights far enough in the correct direction before the small, low-rank parameters just saturate.
That runs out of steam.
It runs out of steam. By decoupling, DoRA lets the optimization leverage the existing magnitude of the original weights while focusing the tiny adapter parameters, A and B, entirely on finding the optimal direction for that policy shift.
It's focusing all the efficiency effort just on the part that needs the most nonlinear change. And the results, I mean, they speak for themselves.
They're stunning. DoRA achieved an overall average accuracy of 46.6%. And to be clear, that not only crushed standard LoRa's 42.5%, it actually surpassed the full parameter fine-tuning baseline of 34.9%.
It beat the full model.
It beat the full model. And this boost was particularly strong on the hardest benchmarks, like the AMC and AMC competition problems, which indicates a genuine improvement in the core reasoning capability.
The implication there is massive for the community. We're finding that the correct geometric constraints, the PEFT method itself, can actually lead to a better optimization outcome than just training the whole model.
It suggests the full parameter space has too much noise or redundancy that the sparse RL signal just struggles to navigate effectively. These geometry-aware constraints are acting as a powerful regularizer, guiding the sparse gradient to the most efficient updates.
And DoRA wasn't the only structural variant that did better. The research also highlighted AdaLoRA and
Yes. AdaLoRA, for instance, uses a sophisticated mechanism to adaptively allocate its low rank. Instead of fixing R everywhere, it uses a process kind of like SVD to figure out which parts of the weight matrix need the most updating.
So it's focusing its small parameter budget where the gradient is strongest, it's spatially aware.
Exactly. It reached 44.2% accuracy. And MISS-SS, or multi-head shared shard, got to 43.4%. It uses a shard sharing structure across different parts of the transformer. The point is, both of these methods incorporate a deeper architectural change than standard LoRa, which just reinforces this idea that innovation beyond the simple additive product is essential.
So the conclusion for any engineering team is clear. DoRA should probably be the new default for verifiable reinforcement learning. But to really understand why DoRA works so well, I think we have to look at the methods that failed. And I mean, failed spectacularly.
This section, for me, gives the most profound mechanistic insights into the RLVR optimization landscape. Specifically, the geometry of the weight updates. We're talking about the catastrophic failures of the SVD-informed initialization strategies, PiSSA and LoRA.
I just want to pause here to emphasize how bad the failure was. These aren't just slightly worse models. PiSSA dropped to a non-functional accuracy of 0.2%.
Basically zero.
And LoRA was barely better at 18.0%. These are results that tell you the fundamental architecture is just incompatible with what you're trying to do.
Exactly. Both methods use singular value decomposition, SVD, of the original pre-trained weight matrix to inform how the adapter matrices are initialized. They're trying to leverage the intrinsic geometry of the pre-trained model.
Yeah.
So why the collapse? We need to talk about the off-principle regime.
Okay, let's break down the off-principle regime because this seems key to understanding the physics of the gradient flow.
So when you look at the geometry of a large weight matrix, you can decompose it using SVD into principal components. These are the directions of highest variance associated with the largest singular values.
So these are the core dominant knowledge pathways the model learned during pre-training.
Think of them as the main high-speed knowledge highways of the model. That's the principal subspace.
Got it. The main highways.
Now, when you fine-tune LLMs with supervised learning, SFT, the updates often align with or reinforce those principal components, but RLVR is different. To successfully learn complex new behaviors like self-correction and math while preserving all that general knowledge, the RL updates consistently localize to the non-principal subspaces.
The low curvature regions.
Low curvature regions defined by the minor singular values.
So if SFT is tuning the main highway, RLVR is trying to subtly adjust the side roads and back alleys to find the truly optimal specialized route. Is that a good way to visualize it?
That's a perfect analogy. RLVR operates primarily by tweaking the low variance, non-principal subspace because that preserved the dominant high variance knowledge it already learned.
Okay, now we can explain PiSSA's spectacular 0.2% failure.
PiSSA, or principal singular values and singular vectors adaptation, operates under the assumption that the most important updates happen where the information variance is highest. So it explicitly restricts the low-rank update to the principal subspace.
The main highway components.
Yes.
That's a direct structural conflict. If the RLVR optimization fundamentally requires the policy to shift in the off-principal space, forcing it only into the principal space creates an immediate catastrophic structural bias.
The model cannot access the geometric space necessary to learn. It's like trying to navigate a detailed side road when the only map you're allowed to use shows the interstate highway system. Structural collapse is the immediate result.
Okay, so PiSSA failed because of a fundamental design conflict, but LoRA is more nuanced because LoRA actually tried to align with what RLVR needs.
It did. LoRA attempted to initialize its adapters using the minor singular components, theoretically aligning itself right in that low curvature off-principle subspace. But it still failed badly, only getting to 18.0%. This failure is less about structural conflict and more about optimization instability.
Why did it fail if it started in the right place?
The problem is numerical reality. The minor singular values, the sigma tail, that define those off-principle components are, by definition, extremely small, nearly zero.
Okay.
So because LoRA initializes the adapter using these components, the initial magnitude of the update matrix is essentially negligible.
So the model starts in the perfect theoretical location, but has zero momentum and has no gas in the tank.
Exactly. When training begins, there's no significant initial bias or direction imposed by the adapter. So the optimization trajectory is immediately dictated by the spectral properties of the gradient itself.
And what does the gradient naturally favor?
The directions of maximum change, which overwhelmingly align with the dominant principal components.
So the strong pull of the high variance gradient flow instantly overpowers the subtle, negligible structural constraint of the initialization.
The model just degenerates right back into the principal subspace because that's where the strongest gradient signals are. This causes instability and a failure to converge. The technical takeaway here is huge. The initial magnitude of the PEFT adapter matters profoundly for sparse RL. You have to maintain enough initial bias to resist the gradient's natural tendency to pull you toward the dominant but wrong components.
What stands out to me here is that these SVD-based methods, which are designed for the dense SFT world, are just fundamentally unsuitable for RLVR. The architecture has to be geometry aware and magnitude robust.
It does.
So moving on from those catastrophic failures, let's look at the other boundary condition, the expressivity floor. We've established that the complexity of math demands a high ceiling, but how low can you push the parameter count before the model just lacks the ability to do what you're asking?
This is a really crucial finding. While some efficiency is good, extreme parameter reduction acts as a structural bottleneck. That sparse RLVR signal, as small as it is, still needs sufficient plasticity in the adapter to capture those complex localized adjustments.
We saw that moderate reduction works fine, like LoRA FA, which freezes matrix A and only trains matrix B. That did fine. It got 43.0%, right alongside standard LoRA.
And that's a strong sign that the sparse reward signal is powerful enough to drive meaningful updates, even if only half of the low-rank matrices are trainable. It shows the learning is targeted and efficient.
But when you push the compression too far, when you reduce the trainable space to simple vectors or an extremely low rank, the capacity just collapses.
Exactly. Look at VeRA vector-based random matrix adaptation. It freezes both low-rank matrices and only learns simple scaling vectors. Accuracy drops to 40.7%.
And even worse?
Even more severely, IA3, which only scales activation vectors, suffered a massive degradation down to 22.3%.
Scaling vectors are just too simple to capture the directional shifts you need, right? If the update needs to rotate the policy in 16 different dimensions, a simple scaling vector can only make existing things bigger or smaller. It can't draw a new direction.
That's the expressive bottleneck.
Yeah.
The complexity of self-correction and iterative refinement that RLVR demands just cannot be captured by mere scaling factors. You need the full low-rank matrix structure, B and A, to provide that geometric freedom.
And this expressivity floor holds true even within the LoRA structure itself, specifically with the rank.
Yes. The ablation study showed that rank 1 LoRA consistently underperformed configurations with moderate ranks, like rank 16 or 32. While rank 1 is appealing for ultimate efficiency, for complex math reasoning, it's a clear capability bottleneck.
Right.
If we're trying to achieve state-of-the-art reasoning, we can't afford to compromise the adapter's expressivity just to save a negligible percentage of parameters. You need that minimum threshold.
So the actionable insight for anyone listening is, stop optimizing for the smallest possible parameter count. Start optimizing for the correct geometric structure and make sure you maintain a moderate rank like 16 or 32 to support the plasticity you need. Less is not always more in parameter-efficient RLVR.
That's the key.
Okay, for these findings to be truly useful, they needed rigorous validation. This section, which you know can sometimes be a brief footnote, is actually essential for proving that these structural insights are robust.
Absolutely.
So let's look at the experimental foundation. The researchers used the DeepSeek R1 distill model families, both 1.5B and 7B. Why those models?
The choice is crucial because they'd already undergone a strong SFT phase, what we call the cold start, which ensures the model has foundational reasoning abilities before the sparse RL signal even takes over.
And they evaluated on a really challenging suite of mathematical data sets, Math 500, AM, AMC. These require structured, multi-step reasoning.
Right, not just recall. And they enforced a structure, requiring the model to use think tags for reasoning and a box for the final answer. This setup makes sure you're grading true reasoning, not just lucky guesses.
And crucially, they use metrics like AVG at K and pass at K to average across multiple generations, which makes the results much more statistically reliable.
Now let's get to the ablation studies. The first striking finding was the remarkable algorithmic invariance of the results.
What does that finding imply for the future of RLVR?
It means the entire performance hierarchy of these PFT methods, DoRA beating LoRA, PiSSA collapsing, completely held absolutely firm across all the tested RLVR algorithms, GRPO, DAPO, Dr. GRPO, so it didn't matter.
That is huge. If the results were algorithm dependent, if DoRA only worked with DAPO, then the finding would be kind of niche. But the invariance tells us something fundamental.
It proves that the efficacy of the PEFT architecture is driven by the fundamental dynamics of learning from sparse rewards, that geometric problem of making localized off-principle updates, and not by the specific nuances of the loss function.
So if you choose a geometry-aware adapter like DoRA, you can be pretty confident it'll work with almost any advanced RL algorithm you want to use.
It simplifies the engineering decision dramatically.
Let's talk about batch size. In the SFT world, there's a strong heuristic that smaller batch sizes often work better for LoRa adapters. Did that carry over?
It did, but the effect was far more muted than in SFT. Reducing the batch size from 128 to 32 only gave a marginal increase in accuracy for standard LoRa.
Why is the effect less impactful in RLVR?
Well, think about the density again. SFT targets are dense. Every token is an information-rich label. A large batch of SFT data can quickly saturate a small LoRa adapter.
But RLVR rewards are sparse.
Sparse and binary. A large batch size of RLVR data is far less information dense, so the small adapter doesn't suffer the same saturation issues, and the benefit of reducing the batch size is diminished.
And interestingly, on one extremely hard benchmark, AME 2024, the larger batch size actually did better.
Which just confirms that this is a nuanced decision. The practical engineering cost of small batches may not be justified by the minimal gain in a sparse RL environment. The focus should really remain on architectural choice.
We should also revisit the LoRA rank ablation, which reinforces that finding on the expressivity floor.
Absolutely. They tested ranks 1, 8, 16, and 32. The results were unequivocal. Ranks 16 and 32 delivered consistently superior results. Rank 1 consistently underperformed.
So it challenges that notion that minimal rank is good enough.
It does. Since the parameter overhead for rank 32 is still orders of magnitude smaller than the base model, the research strongly advocates for maintaining a moderate rank to ensure the adapter has enough expressive capacity.
Right. You sacrifice performance for an efficiency gain that, in the grand scheme of a 7 billion parameter model, is totally negligible. It's a bad trade-off.
It's the definition of a false economy.
Finally, the ultimate test, scaling up. Did the performance hierarchy hold when they moved from the 1.5B model to the much larger 7B model?
Crucially, yes. The consistency across model scales validates that these insights are intrinsic to the optimization process of sparse RLVR itself. At the 7B level, DoRA and LoRa Plus maintain their lead, getting 55.0% and 55.5% average accuracy, respectively, compared to standard LoRa at 54.8%.
So the slight outperformance of DoRA persists, confirming that its structural advantages are robust geometric constraints that make the optimization cleaner, even as the search space grows exponentially.
This gives practitioners a lot of confidence. If they invest the engineering effort into deploying DoRA on a 7B, 13B, or even larger model for RLVR, the performance advantages are going to transfer.
Okay, let's synthesize all of this into some actionable takeaways for the engineers, the researchers, the curious learners listening. If you're building or fine-tuning models using verifiable rewards for complex reasoning, what is the definitive advice here?
The first, and I think the most critical takeaway, is to immediately retire the convenience default. Standard LoRa is demonstrably suboptimal for RLVR. If you're sticking with it, you are actively leaving performance on the table.
So instead, the community should be advocating for and deploying geometry-aware adapters like DoRA.
Absolutely. DoRA gives you a superior balance of efficiency and reasoning capability because it aligns the adapter structure with the intrinsic optimization dynamics of RLVR. especially by decoupling magnitude and direction, just a smarter geometric constraint, and obviously avoid any SVD-based initialization.
Right, given the spectacular failures. So where does the research go from here? The paper points to a few crucial open questions. The first one is about infrastructure maturity.
Yeah, most of this work relies on frameworks like TRL, which are great for rapid testing, but they limit the scope for really large-scale, prolonged RL training. To truly verify stability, we need to migrate to high-performance frameworks like VRL.
And what would that allow?
It would let researchers test how DoRA performs over weeks of continuous RL training under more advanced paradigms like R10, ensuring it's numerically stable at an industrial scale.
So testing them not just on benchmarks, but across the entire life cycle of a production model.
Precisely. The second open question is maybe the most fundamental challenge: mechanistic interpretability. We have strong empirical evidence. We know that structural variants win and that SVD methods collapse, but we need the deeper theoretical understanding.
The mathematical reasons why. Why do structural variants align so perfectly with that off-principle landscape? Why does that tiny initial magnitude in LoRA mean the gradient flow just takes over?
That theoretical framework is what will let us move beyond just modifying existing PET methods and start designing genuinely novel adapter architectures specifically for the unique geometric constraints of sparse RL. That's the path to the next big efficiency leap.
And finally, deployment stability and extending the frontiers. This is about making these gains work in the messy real world.
We need to extend these findings to broader frontiers.
Yeah.
Think about multimodal environments, where RLVR is used to verify an answer based on both visual data and text, or multi-turn interactions, asynchronous RL settings.
All of which introduce huge challenges.
Yeah, huge latency and sample challenges. And on the engineering side, solving practical hurdles is key. Ensuring numerical stability when you merge the weights for deployment, and guaranteeing consistency between training and inference. A PEFT method is only useful if it's reliable when you actually ship the model.
Okay, let's summarize the critical map this research has laid out for us. We started by asking how to efficiently build smarter LLMs for verifiable reasoning. The answer, it turns out, rests entirely in the geometry of the fine-tuning architecture.
The three core insights are now just unavoidable. First, structural variants, especially DoRA and PiSSA, consistently win. They shatter the performance ceiling of standard LoRA by allowing for geometry-aware updates.
Second, SVD-based initialization strategies like PiSSA and LoRA fail spectacularly due to spectral misalignment. They either force updates onto the wrong main highway, or they just lack the oomph to resist the gradient's pull.
And third, there is a clear expressivity flaw. Extreme compression methods, vector-only updates like IA3 or rank 1 LoRA, they just lack the necessary geometric plasticity for complex policy shifts. Efficiency has a minimum cost.
This research really changes our understanding of the trade-off between efficiency and capability. The next generation of AI tools, especially those relying on high-stakes reasoning, where being correct is non-negotiable, will be shaped not by bigger models, but by smarter, geometry-aware fine-tuning techniques.
The path to higher intelligence is now paved with architectural efficiency.
Here's where it gets really interesting. What does this all mean for the next 7B model you use? It means the difference between a high-performing reasoning engine and a bottlenecked, underperforming system is simply the choice of your adapter. The architecture of efficiency is now determining the ceiling of intelligence. Thanks for tuning in to The Deep Dive.
Disclaimer: this video podcast is generated with Google's Notebook LM by Vin Nguyen at VinHex based on research.